Okay, please put away your phones and computers, and let's get started. Okay, so remember the goal, right? The goal is to take your functions and then basically represent them as infinite polynomials, right? Now these infinite polynomials will involve sums of infinite, sequences of numbers, right? So so-called infinite series. Okay, so that's what we're concerned with, infinite series, right? So remember, right? You have some sequence, a sub n, an infinite sequence. Give the sequence, and then you have this thing, the sum of a sub n from 1 to infinity. This is called the series. Okay, and remember that we say that the series converges to L if the sequence of partial sums converges to L, right? The sequence S sub n the sequence of partial sums converges to L. Right, and this is what, right, so we introduced infinite sequences, and we talked about the limit of an infinite sequence, right? We talked about infinite sequences, right? And the limits, and we introduced series, and what it means for a series to converge means that you look at the sequence of partial sums and check if that sequence converges, right? So convergence of series is related to convergence of sequences, right? Convergence of series means that the sequence of partial sums converges, okay? And then one of the important things we did last time was this thing called the monotone. There are two important things we did last time. One was the monotone sequence theorem, which said that if a sequence is monotonic, and bounded, then it converges. Right? Or maybe it's better to say, if a sequence is monotonic, then it converges. It has a limit if and only if it is bounded. Right. But we saw last time that if you're bounded, then if you're convergent, then you're bounded. But for monotone sequences, if you're bounded, then you're convergent also. Right? Then the opposite is true. Okay. And then the very last thing we did was this thing called the nth term test. Nth term test, which said that if a sub n does not go to 0, if the sequence doesn't go to 0, then the series diverges. If the terms of your sequence don't go to 0, don't converge to 0, then your series diverges. Okay. And so that's basically what we did. Very briefly, this is what we did for the last 2 days. Okay. So is there any part of this that people feel confused about? Like people want to hear about? Wangbi, I know you missed the last 2 days, so maybe this is all kind of strange to you. Don't ask me about the whole thing. Don't say, please go over the last 2 days. But yeah, we can talk after, I think. Let's talk after. But for those of you who were here, is there something that was confusing and you'd like me to clarify? Do people understand everything here? Right? We have a sequence, we have what it means to converge, right? Right. So important part, what does the limit being L mean? Right? And then here, this is basically explaining what does this being L mean? Right? And this is basically asking the question, when do certain series converge, diverge? Right. These are the beginnings of tests for convergence. Like you can find out if it's bounded, it converges. If it's not bounded, it diverges. Right? For monotonic sequences, you just need to check boundedness. You know, it'll converge if and only if it's bounded. Right? In general, if you have a general series, then if the nth term doesn't go to 0, then it diverges. But if the nth term goes to 0, you don't know. It could converge or it could not converge. Okay. So that's basically where we finished up. And today we're going to be talking about tests for divergence, for convergence, convergence, and divergence. We'll be basically making up some tests to check whether or not this infinite sum of numbers will converge or diverge. Okay. Okay, and so for today, it'll be only of non-negative series. Non-negative series. So a sub n is going to be greater than or equal to 0 always. Okay, so we're not going to have, there's going to be no negative numbers today. Okay, only 0 and above. Okay. And that might seem sort of strange. Why? How come we don't care about series with negative numbers? We'll have some things to do with them later. But it turns out that this is actually pretty helpful. That most of what we want to do is with non-negative series anyway. Okay, so when we get to the infinite polynomials, it'll turn out that what we want to deal with are non-negative series anyway. So this is the important part anyway. Okay. 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 So first we make an observation. Observe. If a sub n is a non-negative series, then what can we say about the sequence of partial sums of the corresponding infinite series? Okay, I just want you to make an observation, right? Suppose all your numbers are non-negative. Then you look at the sequence of partial sums, right? Remember what the sequence of partial sums is. It's just you sum part of it, right? So S1, sequence of partial sums, S sub n, where the first guy is A1, the second one is A1 plus A2, the third one is A1 plus A2 plus A3, etc., etc. S sub n is the sum of the first n terms, right? S sub n is the sum of the first n terms. Okay. So what do you observe about this sequence? Let me make a simple observation.
Non-negative.
Yeah, these guys are non-negative. So yeah, certainly it's also a non-negative series. It's also a non-negative sequence, but you can say something a little bit better, right? The first one is A1, the second one was A1 plus A2, the second one is A1 plus A2 plus A3. It's increasing, or at least non-decreasing. Yeah, very good. Yeah, non-decreasing, right? You know, it's basically an increasing, right? Because you're always adding on something bigger than 0, right? Every time, like this is S1 plus A1, this is S2 plus A3, right? Every time you're adding on something, and that something is non-negative. Whoops, I should not say non-negative series. This should be non-negative sequence. Right? Okay, you're always adding on something non-negative, and so the S's are getting bigger, right? The S's are getting bigger. It's a non-decreasing sequence, right? It's monotonic. In particular, it's monotonic, right? Okay, monotonic means that you're either non-decreasing or you're non-increasing. Right? Okay, it's monotonic. And so, what do you know? What do you know if A sub n is non-negative, then the series converges if and only if S of n is bounded. Right? Because it's a monotonic sequence. Right? It's a monotonic sequence, and what we said over here is that a monotonic sequence converges if and only if it's bounded. Right? So right. So this right. So the sequence of partial sums converges. Sequence of partial sums converges if and only if it's bounded. Right. Everyone okay with that? Anyone confused? Actually, talk to somebody nearby for 1 minute and just see if you can talk about this and ask each other questions. Wangdi, why don't you sit with Dijela and these guys? Sit over here. I think they'll be helpful to you. You missed a couple days. Okay, everybody. Now does anybody have questions? Does anybody have questions? Is it clear to everybody, or does anybody have questions? Okay, so I hope it's clear, right? So remember, right, for the infinite series to converge, that's the same thing as saying that the sequence of partial sums converges, right? Now, we just said the sequence of partial sums is monotonic, right? And over there we said if you're monotonic, you converge if and only if you're bounded, right? So that's all that's going on here, right? The sequence of partial sums converges if and only if the sequence of partial sums is bounded, right? In other words, the series converges if and only if the sequence of partial sums is bounded. Okay, so this will give us this observation here. This observation here is going to give us our first convergence test. The first convergence test is going to be called the integral test. So, for example, here's the statement: if f is continuous, decreasing, and positive on 1, infinity, then the infinite series f of k from k equals 1 to infinity converges. If and only if the improper integral f of x dx from 1 to infinity converges. Okay, so to check convergence of a infinite series, it suffices to check convergence of a related integral. Okay, so let me give you an example. Somebody says, does 1 over n from n equals 1 to infinity converge? Right? Does this converge? And what you say is, well, let f of x be 1 over x. Okay, so 1 over x, right? So yeah, this. Right? Okay, so right, what you see is that f at 1 is 1, f at 2 is 1 over 2, f at 3 is 1 over 3, f at 4 is 1 over 4, etc., etc. Right? Okay. And so what the theorem says is that this converges. This converges if and only if the improper integral converges. Okay. Now, does this improper integral converge? Does this converge? No, it doesn't, right? Right? Since this thing diverges, we know that summation 1 over n diverges. Okay. In fact, we saw this yesterday, right? We saw yesterday. This was the harmonic series, right? We saw yesterday that although this thing is growing really slowly, it goes to infinity, right? And this is another way of saying that. You say, well, the convergence of this is equivalent to the convergence of this, and this thing diverges. Ongo, do you have a question?
The limit of it is 0 and divergence.
That's right. So even though the function goes to 0, the integral diverges. Right? The integral diverges. Right? Because you remember how you calculate it. Right? You say, well, I need to take the integral from 1 to b. I get the natural log of b minus the natural log of 1. And I take the limit as b goes to infinity, right? And the limit goes as b goes to infinity of this is going to be infinite, right? So even though the integrand goes to 0, the integral diverges, right? Right. In fact, you know more than that, right? Suppose we say this for p greater than 0. For what p does this converge? You should know this already, right? Who knows the answer? P bigger than 1, right? Because from the integral test, we know that this converges if and only if the integral of 1 over x to the p converges, right? Right. By the integral test, this series converges if and only if this improper integral converges. And we saw earlier by calculation that this only converges when p is bigger than 1. Right? This converges if and only if p is bigger than 1. So that tells you, for example, that if I look at 1 over n squared from n equals 1 to infinity, then that actually converges. 1 over n diverge, but 1 over n squared converges. Okay. In fact, it's interesting. It's actually a very interesting fact that this converges to a number, pi squared over 6. Okay, but we can't show that in this course. You have to wait maybe 3 more courses or something. You have to wait maybe 3 courses, or around 3 or 4 more courses until somebody can explain to you why this is true. So I'm just going to erase it. What we do know is that this is finite. Okay. What we can explain in this calculus class is that this is finite, because the integral test says that this is finite if and only if the integral of 1 over x squared is finite, and that is finite. Okay. Let me give you a problem. Find out if 1 over n, natural log of n, converges. Does it converge or diverge? Okay. So take 1 minute and see if you can do it. Just check it. Okay, turn to somebody nearby and say yes or no.
No.
Okay, who says it converges? Who says it converges? Continue. Who says it diverges? Tin and Hall. And everybody else doesn't know. Doesn't want to say. Okay. So Antony, tell me what we need to do. So we need to check the integral, the convergence of this integral. Oh, there's trouble. Actually, let me say from 2. Sorry, it should be from 2 to infinity. Because one doesn't make sense, right? If I put in a 1 here, I get infinity. Use what? Derivation? Differentiation? Derivative? Derivative? Yeah. Yeah. Okay. So I mean, how do you integrate this? How do you like? This is going to be, of course, the limit of 2 to b goes to infinity. You know, this, right? But how do you integrate? How do you integrate this? Okay, so you've got 1 over x, 1 over natural log of x. Yeah. Right. How do you integrate it? Somebody tell me how to integrate it. Those of you who have been in this course. Let u be natural log of x, right? Du is going to be 1 over x dx, right? So this turns into the integral from 2 to infinity of u to the minus 1 du, right? Which is the natural log of u. Wait a second, I'm not sure where it's from. From when x is 2, this should be natural log of 2 to b, so natural log of b. Okay, so we get the natural log of u between natural log of 2 and natural log of b, right? So we get the natural log of b minus the natural log of the natural log of 2. Right? And we take the limit as b goes to infinity, and you see what happens, we get infinity. Right, so this diverges. The integral from 2 to b, 1 over x ln x dx. We do the use, we change the variable, we get this. Okay. 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 Do you want to do another practice? Let's do another practice. Okay. So let's say same sort of thing, but now we're going to go from n natural log of n squared. Okay. difficulty, turn to somebody nearby and talk with them. Okay, so what's the answer? Does it converge or does it diverge?